Okay, so like I was saying here, you expect a smooth curve to be smooth, not have kinks in it. Something like this over here, where you have it jumping at one spot to another. It has these zigzags. Those are times that the position functions, f of t, g of t, are making sudden changes. They're making very sudden changes there. And sudden changes means discontinuous for derivatives, right? They can't both, if a curve is smooth, their derivatives have to be continuous over this interval, and they have to be never simultaneously zero. It's okay if one of them becomes zero. Okay, it's okay if one of them becomes, because that could be something like this, where it could go and then start going like that, or y is not going up or down, so the derivative is zero, right? But x is, right? And for that matter, anytime it goes in a straight line in any direction, the derivatives of x and y are zero. So, okay, except possibly at the endpoints. So we're going to allow it to get away with the endpoints, because endpoints are going to be the no-no points of these intervals. So, and then we call a curve C piecewise continuous, or piecewise smooth, if it is smooth on a bunch of subintervals. So in this crazy one I just drew, right, looks like it would be smooth from here to there. And then that's one piece. It'd be smooth from there. Now I get into trouble. To there. That's the second piece. And then I'd have to go here. That's the third piece. That's the fourth piece, right? This is the fifth piece, right? All of those, it's smooth over all those subintervals. So you could break up, the definition of this curve into subintervals over which the parametric representations were smooth. So we call that piecewise smooth. All right. All right, a couple of examples here. Is the curve defined by each set of equations smooth, piecewise smooth, or neither? Okay, smooth, piecewise smooth, or neither. Well, what are we looking for? We're looking for places that the derivatives are simultaneously zero, or places where the derivatives are not continuous. And now, so what are the derivatives here? Well, y prime is an easy one. Right? And n equals 0 at y equals 0, right? And then up here, no. T's. It equals 0 at t equals 0. How about this one up here? What's the derivative of the absolute value of t? We didn't cover that derivative, did we? Right, there's not a formula for it. Well, it turns out that the absolute value is and we did talk about it. It is that, and like that. Right? And so the absolute value of x is just x if x is greater than or equal to 0, and it's negative x if x is less than 0. So there's two pieces. On this part, y equals x. On this part, I'm going to do something lazy. It's hard to write that angle, so I'm going to do this. Here. No, I'll turn it. right? Right? Question. What's the derivative? Derivative is the slope, right? So over here, y prime equals 1. Over here, y prime equals -1. What about here? We actually did this very problem back when we were doing derivatives. Right here, the derivative is undefined. So y is absolute value of x is not differentiable, not diff at x equals 0. Okay. And so back over here, f prime and g prime are continuous on I. So it is, we have to say here, x prime of t is discontinuous at t equal 0. So we have a problem at 0. We have a problem at 0. And so we, we could define this piecewise, it's piecewise smooth, okay? Because from 0 to -infinity, or -infinity up to 0, not including 0, it's smooth. From 0, strictly greater than 0, t greater than 0, it's smooth. So, but it is not smooth, it's piecewise smooth. This is piecewise. Right? Down here is the graph. Now you'd expect the x part to always be positive, because you're taking the absolute value of t, so it's only going to be on the positive side of the x's, right? Y can be positive or negative. But you see that you have a problem right there. You see you have a problem right there.
So do they always have to be both, like piecewise, or
No, it could be neither. But
could it be neither, or could it be either or? Like
it is, well, well,
the other?
okay, yeah, good question. Smooth, it can either be smooth or piecewise smooth. Because if it's piecewise smooth, there's points at which it's not smooth. So the answer is it's either or. And then neither could be neither. Now, neither is a very hard situation, because you have to find a function that is either continuous, not continuous, or not differentiable on any interval. It turns out the neither, examples of neither are pretty contrived. Don't worry about that. But yes, it's either or. This one we already looked at, right? So our derivatives, actually we looked at the opposite one with the cycloid. We had x equal cosine, y equal sine. And the interesting part, if you swap them, does it make a different graph? Well, over here you see it doesn't. It doesn't make it a different graph. It will trace it different, but it will not make it, it will not, if I do it just from 0 to 2 pi, it won't. So is the curve defined, is it smooth, piecewise smooth, or neither? Well, x prime is cosine t, y prime is negative sine t, and those are continuous everywhere. Everywhere, but there's a second condition. They got to be continuous, and they're never simultaneously equal to 0. at the same value of t. So these are smooth. Those are smooth. Okay. Well, we're going to do more of that later. Parametric equations and calculus. We're finally going to do some calculus. Well, actually, we did a little calculus here. We had some derivatives, right? You know what? I just might. You know what? I'm going to jump to this example. I'm going to skip this one. Just in the interest of time, get to some stuff that is, I can always come back to it, right? I want to get, that's the graph, by the way. You're asked to graph this and to find the equations of the line tangent to the curve at 0, 4. And it turns out to have 2 tangents at that point. Yeah, so it's a trip into some rigor, and it's not so bad. I may come back to it, but skip it for now. Arc length in parametric form. We did arc length. You remember arc length for, remember if you had y equal f of x, right? The arc length was what? Little s equal integral a b square root 1 plus f prime of x squared dx. Recall, we've had that. This is when it's in parametric form, okay? Now, remember in parametric form, you have your equations in this form. Right? And so you take their derivatives, square them, add them together, and you have to integrate what's left, right? Find the circumference of a circle of radius a. Well, the hardest part here might be just finding the equation, but we've done that. We did that. That's one benefit of going through that cycloid, is we came up with x of t is cosine t, y of t equals sine t. And something that's important, if you let t go unbounded, that keeps going around the circle. It's going to have like an infinite length, right? You just want one trip around the circle. And one good thing the calculator, working on the calculator did for us, is we had to set our bounds of t. We had to be conscious of what t was. Or it only drew half the graph or something like that. We had to be conscious of what t was. So we saw that this started at here, t equals 0. And then goes around once, and ends there at t equal 2 pi. That's one trip around, right? And by the way, if you haven't noticed, these have direction. That's going to be very important in chapter 11. Because in chapter 11, x of t and y of t are going to denote position, and their derivatives is going to be a velocity function, right? This is going to be a trip into physics a little bit. And the derivatives of those are going to be acceleration. In chapter 12, we're going to get a lot into velocity and acceleration in chapter 12. Chapter 11 and 12, 11 is going to be fairly easy for you if you've had the physics with calculus. Chapter 12 will be, well, I don't know, depending on what Dr. Kite did. It might be easy for you too. But you're going to be decomposing things into velocity and acceleration vectors. Anyway, here we're doing the arc length, right? And so x prime is minus sine t. Y prime is minus cosine t. Sorry, positive cosine t. Okay. All right. And so what's our arc length? It's going to be s. It's going to be integral Now, look, you're integrating the arc length for t in a certain interval. T at a certain interval, okay? So it can't intersect itself. That's another thing. If it intersects itself, things get crazy. Because what will happen is that, like, if you make like a figure 8, the arc length gets a little weird, all right? But you can do it. You just have to do it piecewise, part half one side, half the other. And so this is going to be integral from 0 to 2 pi square root. Well, what is dx dt? That's this. What is dy dt? It's this. Okay. All right. Well, what does this equal? This is not particularly sophisticated, right? And this problem, it's setting it up. This is just walking through the setup, right? Well, that equals 1. And so this boils down to 0 to 2 pi dt. You're getting 1. That equals t from 0 to 2 pi, which is just 2 pi. And miraculously, that is the circumference of a circle, radius. Oh, wait a minute, you know what? I caught myself. This would be the circumference of a circle of radius 1. I got too fast. This isn't a circle of radius 1, it's a circle of radius a. So how does that change this problem? Well, that's going to be an a here, an a here. We did that last time. We put 2's there last time. So the derivative is going to be minus a sine t and a cosine t. Squeeze this and let's go like this.
Is there a reason why you just put in pi instead of 2 pi? I'm not one.
Oh. It is a desperate need of a second cup of coffee. No. Let's say another cup of coffee. My second cup was a long time ago. Thank you. Yeah. I forgot the A part. I didn't do what I tell students to do all the time. Be sure you're answering the question. Sometimes you see tons and tons of work, but they never get around to answering the question. Okay. Surface area. And this is of a surface of revolution. So you're taking a curve and you're revolving it around one of the axes. Now we did this for, remember disk method and shell method? In that same section, we did surface areas of functions like y equal f of x, spun around the x-axis and y-axis. This is a little bit different because if I'm going to revolve around the x, which is g of t, should stay up there in the stem. If that doesn't cross itself on that interval, then the surface area of the surface revolved by forming C about the coordinate axes revolve is given by the following. This is interesting. What this is doing here is if you have a parametric curve and it can't cross itself, this G of T is our mystery here. What is the G of T? What is the F of T? Well, it is going to be like a radius function. And I am surprised that it's not more spelled out here. Oh no, here you go. Right here. Duh, right in front of me. All right. All right. So now if you think about it, when you're revolving around the x-axis, it's the y value becomes the radius. Now follow me there. Let's just take a look at this top. Suppose I have some curve. I have a parameterization of this curve, right? And so this is x equal f of t, y equal g of t. Well, it's going to get revolved from, say, points A, points B, point B. And so it's this section here that's getting revolved, this section here. Right? And so when that gets revolved, that, you're going to have a this, right? And then you're going to have something like this. And then you're something like this. The reason why this G is here, this is what I started to say before I noticed the notation, is it's the radius from here to there is G of T. So it's the radius at any point along there, okay? And so you have 2 pi radius. This is like 2 pi r. Right? 2 pi r is the circumference of a circle. And then this part accounts for the fact that it's going in and out. And so it's going to be a little longer. Unless you have a cylinder where it goes straight across like that, it's going to be a little longer accounting for the arc length, right? So that's what's going on there. So find the surface area of a sphere of radius A. Well, we have to parameterize it. And there's more than one way to do this, right? So a sphere of radius A, I'm interested in the surface area. And so I could take this curve, that curve, and revolve it around the x-axis, right? And so that would become make that bold. And so as it gets revolved, it's going to be like this, right? Right? And so it's going to be like this. And it's going to have a radius of A. So this point right here, this distance here is A. So it's important to note that we're revolving this bold section. We're not revolving a whole circle. We're revolving half, the top half of a circle. And so it's going to be, the radius of that top half of the circle is, x is going to be a cosine t. Y is a sine t. The interesting part is that t is only going to go from 0 to pi. 0 to pi. No, that's not really edited down. Now we can see it. Right? If I did 0 to 2 pi, I would be doing the bottom half of the circle too. And when I revolved it around, I would get double the surface area. Right. So, according to what we have up here, our radius at any point from here to there is g of t, which is the y, a sine. That's important. So now we're ready to go. Now we're ready to go. S is 2 pi on the outside, integral 0 to pi. And then the g of t, a sine t, square root x prime t is minus a sine t. Y prime of t is a cosine t. So in here, I have a minus a sine t, a cosine t. That's the part I want to make extra sure you understand. Because as usual in these problems, it's the setup that takes the most time. And my board, I just sits it lagging and it's about to crash. So we're going to back out of that. 33. And then back in. Crash recovery. I told you I felt it. Let's see how much we lost. Not bad. Okay. Okay. All right, where were we? Over here, we have to rewrite this. 2 pi integral. This a can come out, so I'm going to put that one a and that a out there. And sine t 0 to pi square root a squared sine squared t plus cosine squared t dt. Like last time, this equals 1. I probably ought to put in examples that are more robust on this, but my goal is just to show you the method. So this whole thing here, all of that just equals a. So that makes it a squared on the outside. Right? And then I'm going to have integral 0 to pi sine t dt. Pop quiz, antiderivative of sine. The derivative of what is sine? Fill in the blank. What is the derivative? The antiderivative of sine. You're tempted to say cosine. The derivative of cosine is negative sine. So this has to be negative cosine. And that's going to be what? 2 pi a squared. Plug in pi minus cosine of pi minus cosine of 0. And I don't like something here. I'm not liking something here. What I'm not liking is, oh, we left off a negative. I didn't like this is going to be 0. That's what I didn't like. But that's a negative cosine. There needs to be a negative right there. So those two cancel out and become positive. Now we're good. Because cosine of pi is? What's cosine of pi?
One,
Close.
0.
Close.
It's somewhere.
Pi is over here.
So
Cosine is the x-coordinate.
negative 1?
Yeah. Right. Negative. Draw those unit circles. No shame in drawing unit circles. Draw them all the time. You see me draw them, right? So this is going to be, go back to here. Here, 2 pi a squared. That's a minus, cosine of pi is a minus 1. So that's minus of minus 1 plus a 1. That equals 2. And that equals then 4 pi a squared. And we've derived that about 4 different ways now, right? surface area of a sphere radius A, surface area, not volume, surface area, is 4 times this area of a circle of radius A. All right? The good news is I'm not putting any homework in these. I get to put homework in these slides. I don't know why I don't have homework there. You've got to go to these sections and do some homework in the book. There's tons of them in the book. All right. Now we're going to go into some trig. A lot of the rest of what we're doing is trig between now and Monday. Okay. Polar coordinates. Have you ever had polar coordinates?
They sound familiar.
Okay. All right. All right. These are taught in most trig classes. Problem is that no one's had a trig class. Trig is like a unit in some pre-calc class or whatever, and they don't a lot of times get to this. All right. Well, I should put a slide before this. Why should I put a slide before this? Because if I have a point up here, X and Y, right? The way we arrive at it is we go out X and up Y, right? Okay. That's like going to Walgreens, right? You're down Blackburn and then Western Nobs, certain amount one way. Another way, we can't do it, but birds would be to go find an angle for Walgreens and go straight. So that means this way. You find what angle this is here, we call it theta usually, and we go a certain distance that we call r. That's another way of representing that point. R theta. Okay.
So that wouldn't just be called the hypotenuse?
Yeah, absolutely. Yeah. So you're getting I'm gonna chase that because you just noticed that r squared is going to equal x squared plus y squared. That's what you just noticed. Right? All right. What is theta? Well, theta is going to be a little trickier. Theta, we're just going to get to this, but since you mentioned it, I can blame it on you. From any slide, you can go a bunch of different directions, right? It's not like there's only one right direction. And when a student mentions a direction, it's perfectly legitimate. That means the student's dialed in on that. That's the time to chase it. Theta, we're going to actually, we have to relate theta. In fact, we have to relate r and theta to x and y. R and theta have to be related to x and y. Theta, we define it in terms of tangent. It is the arctan. It's the angle whose tan is y over x. Right? Now we can go the other way. We can go the other way. This is r and theta in terms of x and y. What are x and y in terms of r and theta? You related r in the hypotenuse. Okay? This is theta in terms of x and y. But we got to do the other way around. This y, what is it equal? In terms of r and theta. Well, if you know basic trig functions, this is going to be opposite, right? Opposite over hypotenuse is going to equal the sine of theta. Opposite is r. Excuse me, y. Opposite over hypotenuse is the sine of theta. Right? This is opposite. This is hypotenuse. Well, that means that y is r sine theta. Similarly, this distance here is x, right here. X divided by the hypotenuse is cosine theta. That implies that x equals r cosine. Now there's a slide coming up here, but now you know how to get, just from that discussion, you know how to get from x's and y's to r's and thetas. If I hand you x's and y's, you plug them in here and you hand me an r and theta. If you hand me r and theta, I plug them in here and I hand you back x's and y's. See? All right. So they are two ways of doing the same thing in that aspect. Well, in the other aspect, you're going to see is British Calc 3. There are much easier ways of describing certain things. There's easy ways and hard ways of describing certain mathematical constructs. And when we're doing integrals and stuff, we want the easy way. Right? We're bottom dwellers. Okay. All right, so here's some examples. A lot of times, these are just concentric circles of radius 1, 2, and 3, like a target, right? And so if we go out pi over 3 and out 2, that is r theta, 2 pi over 3. Right? Makes sense. I usually don't use stuff in the book, but since this is done so neatly. Down here, 3, you go out 3, and minus pi over 6. That's in the negative direction. It's also, you could count that minus pi over 6. You could measure that angle this way as 11 pi over 6. So there's more than one way of representing every point. In fact, I could go around 2 more pi, and whatever that angle is, what's that, 23 pi over 6? That means you go around once and then 11 pi over 6. That would be another angle. There's infinitely many ways of representing most points in polar coordinates. Infinitely many ways. And generally, the techniques always work, no matter which one you use, but sometimes not. You gotta be careful. All right. One we didn't do here. We should do another. How about this? How about if that is pi over 3? What would this angle be? That angle is 4 pi. Right? So another way of describing that point up there, like for example, to go to Walgreens, let's just say, be simple and say it's a mile. Okay, straight distance to Walgreens. So I go whatever angle, and then I go a mile. Right? Another way of describing that point, I told you, would be to go all the way around the circle once, and then that angle, then go a mile. There's even other ways. Another way is, how about if I go, instead of that angle, I go from here, not to there, but to here. And I go backwards. I go negative radius. So that point would be 4 pi over 3 but with a negative radius. You can have negative radii here. Right? It's another way of doing it. So these are the things we just derived on the other screen. Right? this is the same as, this here is the same as saying theta is arctan, which is what I said on the other screen, right? So convert these rectangular coordinates into polar. So we're told those are rectangular, so this is the x, this is the y. Convert them into polar. Right. Now r is going to be square root x squared plus y squared. And that's going to be the square root of 2 squared plus 3 squared. And that is what? Square root of 13. Y, or excuse me, theta is the arctan of y over x, 3/2. Now, whenever working with trig in here, arctan is the angle whose tangent is 3/2. That turns out not to be one of the convenient angles. Right? If I tell you arc sine of 1/2, you'd better be able to come up with pi over 6. Okay? It's a convenient angle. Multiples of pi over 6, multiples of pi over 4, those are all convenient angles, right? But something like this is not a convenient angle. So that's just an angle. And so our answer is here, r theta, r square root of 13, theta, arctan, convert that polar point into rectangular coordinates. You're told that's, oh, it's kind of negative. Now, those are angles we know about. Maybe a graph would help. You don't have to do a graph, but maybe one would help. Because over here, 2 pi over 3 is where? It's going to be around right here. But you're going to go negative 4. You're going to walk backwards. And so that is going to be like that. And so our final point is going to be down here. And so when we convert this rascal to rectangular coordinates, we expect the x to be positive and the y to be negative. Right? Now, in fairness, you don't even need those formulas. Because if you know basic geometry, you could go like this, like that, right angle, right? And so this angle here would be pi over 3, which is 60 degrees, right? This is 30 degrees down here. And you could use what you know about the ratios of triangles. So for example, 30, 60, 90 triangle have the sides have the relationship 2, 1, square root of 3. Right? That's one you should know, right? And then, of course, if you have a 45, 45, 90, right? That should be, that's the ratio. Well, so one crude way of doing this, and we're going to do it the right way here in a second, is that if I make this here, if I multiply all these by 2, and I make that a 4, and that's a 2 squared, it's a 3, and that's a 2. Then that tells me that the angle opposite to 30 degrees is 2. So here's 30 degrees. The angle, the side opposite, I meant to say, is 2. The side opposite to 60 is 2 squared, it's a 3. And since that's a negative y, we're going to put a negative. And so that should be our answer. Our answer should be our x and y. That should be 2 minus 2 square roots of 3 should be our answer. All right? And that's just using geometry without those formulas that we have. But we have formulas. So we're going to use the formula. Right? All right. What's cosine 2 pi over 3? What did I tell you to do? Do the unit circle. 2 pi over 3 is like right there. That point, it's going to be minus 1/2 square 3 over 2. So the cosine is minus 1/2, right? And so that's going to be minus 4 times minus 1/2 is 2. That's our x. That's what we got the other way, right? Our y is our sine theta is minus 4. Sine of 2 pi over 3. What's sine of 2 pi over 3? The y coordinate there. The y coordinate there. Right? And this is going to be minus 4 times square root of 3 over 2 is minus 2 square roots of 3. So we have 2 minus 2 square roots of 3 for our answer. We got the same thing either way. One of them was without using the formulas we had before. But these are very important to know. Those are very important. So basic graphs. Graph. We're going to do some graphs. Polar graphs. Now, first a principle. Here's a principle. You already know this principle. Ready? Let's go down here. What does the graph on a coordinate grid y equal 2 look like? What does that graph look like? Yeah, it's a set of points that has y coordinate equal to 2. So you go up here, well, if this point is 3, well, that point is on, that's 3, 2. That'll be on the line, right? Minus 1, well, that one's on the line. Any point that has a y coordinate 2 is on the line. So you get that, right? Same with x's. X equal 3, same thing. Good. Now here's the principle. Y equals 2. You get a point on it, and the missing variable was x. It sort of slides in the x direction. It slides through all values of x. Any value of x will work as long as y is 2. You get that? It kind of slides in that direction. Same here with the red line. X is 3. It slides in the y direction. So the key, the principle I want you to get, you got to get this, is it slides in the direction of the missing variable. Okay. So I'm going to put it here. That's crude, but graph slides in direction of missing variable. That's key. That's key. Key. So you find out what, okay, you go up 2 for y equals 2, and then you slide it from there. You went out 3 for x equals 3, and you slide from there in the other direction, up here. R equals 2. What's missing? Theta. There ain't no theta. So we're going to do up here. Here we go. Graph any point with radius equal to 2. Any point. Suppose we do that one. It can be any point. It's going to slide now in the direction of the missing variable. So any point that has a radius 2 is going to be on this graph. So, well, that one is, right? This point over here, right? Theta goes throughout all values of theta. So theta sort of goes through all of its values. And so what you wind up with is the locus of points 2 from the origin. It's a circle. So R equals 2. It slid in the direction of the missing variable. This one is a bit trickier. Just a little bit. Just a little bit. All right. Pi over 3 is where? Well, it's kind of in that direction, right? Like here. That's pi over 3. Okay. Question, what is R? R is anything. So that point will be on the graph. This point here is on the graph. This point way up here is on the graph. Right? This point down here is on the graph. That would be a negative radius, right? It's some negative radius. This point way down here is on the graph. Any radius, so radius can go from minus infinity to infinity. It slides in the direction of the missing variable. And so you have this point, you let it slide. You got to keep theta equal to pi over 3, though. And so that winds up being a line. Right? That winds up being a line. Now, it turns out you can graph any line in polar coordinates. I wouldn't necessarily recommend it. This one, the ones through the origin are exceptionally easy because all you need is their theta that they make with origin. It turns out, we're not going to do it now, but that graph there, y equals mx plus b, I can graph that in polar. For one thing, I know what x and y are in polar. Right? So we're not going to do that. We're not going to do that. But that is a well, I'll put it this way, we're not going to do it now. Not going to do it now. Slope in polar form, we're not going to do it. Not going to do that. The function of a circle of radius 1 in polar coordinates. Well, we could do r equals 1. That's one way. You know what I think we should do with radius 1? I'm going to do here. Centered. I'm going to add this. Let's center it at 1-0. What's that gonna look like? Oh, we're out of time. You know what? We'll pick it up Tuesday or Monday. No, Tuesday. Monday's test.
Yeah.
Next test. So I saw you already had your appointment made, even for the finals too. So good on you. Appreciate that.
I have a question. Do you know the unit circle tricks of how to find the coordinates without having to draw the unit circle?
I